recorded here. So welcome everybody. So we're going to get going. See if breakout rooms work today. Okay, so we're talking about Milestone 1. So we talked about that some yesterday. We're going to talk some more about it today and then move on to some ideas on how to get your team working well together. So m1.h is this header file that we've given you, and it's the specification of what you need to build in this milestone. And near the top of that header file is this key information that different functions have different speed requirements. So you're going to find a bunch of functions like this one. Here's one called find street segments of intersection. So you pass in an intersection ID, basically an integer, and it returns a vector of other integers. Those integers are the street segments, the IDs of the street segments that form that street. So remember that a street is many blocks long usually, so we get a whole bunch of street segments that together form some street. Like I just drew a representation of Bloor Street. So you pass in ID 500, for example, maybe that represents Bloor, and you get back a vector of, for Bloor you might get back a vector of 200 street segments that represents all of the pieces of Bloor Street that are city block long. Okay, that's what we're trying to build, and you notice that it has this line. It says the speed requirement is high. So you say, well, what does that mean? It means this function is going to have to not just pass per functionality, so return the correct answer, and we will test that, but also pass some performance tests. So it's going to have to do it in a certain amount of time. And to figure out, well, what does high mean, you go earlier in the header file, and you see this. So functions that have a high speed requirement, well, maybe I'll start from the bottom. Functions that have no speed requirement, we only have functionality tests. We don't care how fast they are. Our tests time out after 5 minutes, so if you actually take longer than 5 minutes to respond, we'll consider it hung and you'll fail it, but otherwise it's okay. Moderate means we're going to speed test it, but we think that you can, when we call this function, you can construct the answer by making calls to the lower level API that we provided, the Streets database API. You can construct the answer, return it to us, and as long as you do that in a reasonable way, you should pass the speed test. And then there are some functions where we say the speed requirement is high, and this is one of them. We said this one's high. Okay, so high, the speed requirement is fast enough that we don't think you're going to be able to pass it if you just try to construct the answer on the fly by calling our lower level API functions. We think that you're going to have to create a data structure and basically pre-compute some things. It's up to you to decide what to pre-compute, so then we actually query you, you can give us the answer faster because you've actually partially or completely constructed the answer in advance. Okay, so let's look at what kind of report you would get from ECE 297 exercise, which is the test program that will connect to your library that you're writing in this milestone and test it. So if you run ECE 297 exercise, you'll see that there are a whole bunch of tests, and they're grouped into categories called test suites. So we've got this test suite says, well, it says it's a public test. That's why you're able to run it. There are also some private tests we run that are similar. They're not any harder. They're just different. It's for Milestone 1. And this one's testing functionality. So it's just checking if they get the right answer. And these are things testing having to do with functions that compute something about distance or time. And you passed all those. So that's great. You also see there's some tests that have this performance in them. So this says performance test. It's related to something about intersections. So we just kind of group the tests in ways that we think make sense. And this particular code that is our reference solution passed all this performance tests too. So, but when you first write some function, you're initially going to fail everything. So you're going to fail the functionality tests. Then you're going to eventually fix your bugs. And you're going to pass that. And then you'll probably fail the performance test for a while. Okay, how do we set these performance targets? You're writing a low-level API in Milestone. Well, you're writing a higher-level API than the one we gave you, but it's still lower level than providing functionality that an end user kind of wants to use. You're building utility functions that will be helpful to you. So one way you can set speed requirements is you can check, well, what does the end user need? But we can't really do that in this case because we don't have an end user yet. You're building utilities that the rest of your program is going to call. So the approach we take instead is basically an STL-like approach, standard template library-like approach. For the functions that we care about, that we know are going to be important to be fast later, or some of them just as a good programming exercise, we basically say you should get the lowest complexity, big O notation, that you can. And that's actually the way the STL is created. The speed targets for the STL are just best big O notation for this kind of data structure, because they have no idea what are all the things people are going to do with a vector or an unordered map. So they just say you have to hit these complexity targets. So that's basically what you have to do for the high performance functions. You're going to have to, we're not going to check this. If you pass the performance test some other way, it's okay. But what we expect you have to do is you have to allocate some data structures, and you should choose data structures with the best big O complexity for the kind of function you're trying to build. So it's up to you to choose, well, what is that? What's the logical data structure for that function? So in terms of required performance, there's a load map function. And the load map function, I'm going to talk about in a little while, but before we call any of the other functions that your library provides, we will always call load map. So load map lets you load in data that our API needs. There's a function call to basically load our low-level API. You got to make that function call. There's actually two of them, so make those two calls. And then you can load up some more data if you want. And it can be pretty slow. So the complexity of load map can be order n, where n is the number of intersections or street segments in the city, so hundreds of thousands, maybe even millions for Tokyo. And in terms of absolute time, it can be several seconds. So you've got quite a while for load map. You shouldn't have many problems passing the load map speed tests. The more challenging performance requirement are these high performance functions. And again, you need to use the data structure or algorithm that leads to minimum or nearly the minimum big O notation. And in terms of turning that into a number, the ECE 297 exercise tests test against a specific speed requirement, a specific time in milliseconds or seconds. Those times we set by, we basically write a good solution. So we know how to write solutions that use the best data structure for various problems. We time that, and we give you 2.5 times as much time. Okay, so you don't have to micro optimize as long as you're using reasonable data structures and you don't do wildly inefficient things in your code. You're going to pass the speed tests. Okay, so you don't need to spend a lot of time micro optimizing. Okay, so I'm showing you an example of basically the main program that you haven't learned about this yet, but the unit tests are running. So ECE 297 exercise is an example of unit tests. It's directly connecting into your functions to test them in a way that essentially is efficient for test. It's not the way an end user would try to run your program. And the way ECE 297 exercise works, it basically is building a main function automatically and running it. And in that main function, we always call load map for any test. So here I'm saying load map for the Toronto binary database. So we're going to load Toronto. And then we're going to do a whole bunch of tests. So for example, I might call, one of the functions you're supposed to write is find closest intersection. So we pass you a position, a latitude and longitude position, and you're supposed to return the ID of the intersection that's closest to that. We know for this map, maybe we gave you a latitude and longitude of 45.2 degrees west and 46 degrees north. And we know that the intersection closest to that in Toronto has this ID. So in our tests, we check, did the intersection ID that you just found match that? If it doesn't match, you failed the test. We'll record that, and we'll give you a summary when the test is complete. And we'll do this a lot. So we're not going to test just one intersection. We're going to test a whole bunch of them. After all of these tests have run, our unit test, this ECE 297 exercise, will call your close map function. Okay, so close map is your function. Find closest intersection is your function. load map is your function. The rest of this code is ours. We wrote the test driver. It's in ECE 297 exercises calling your code. So basically, for these high performance tests, you need to load something in load map, and it's up to you to decide what it is. You use it to make some functions faster wherever you need it to. And then we're going to check for memory leaks. We run valgrind on your program. Also, sometimes we might run one city and then another city afterwards. So we might call load map in Toronto, run a bunch of tests, close map. Then we might call load map on Moscow, run a bunch more tests, call close map. So it's important that this close map clean up whatever load map did. So load map creates data structures, close map tears them down. So gets rid of all the memory, so there are no memory leaks. And if you have another test on a different city coming right after this, that you're back in kind of a clean state. Okay. Let's see. So you won't do load map before you do a close map. We will do load map. Well, we'll never do two load maps in a row. So I see a question in the chat. We won't do load map before you do a close map. We will always do one load map before we call close map, because that's kind of the convention. You load a map and then we can ask you to unload it. We will never call load map and then call another load map here without a close map in between, because the convention we're using is that there's only one city allocated at a time, so you don't have to support having two cities in memory. We'll never query you. It's not even clear what our calls would mean at that point. Does that make sense? So you can definitely assume that. Question is, does the 2.5x speed requirement get tested here? Basically, if we have multiple tests. The functionality tests just look like this. They just check for correctness. There's no speed. The ones that say performance have some more code that I haven't shown you here, but you'll see when you look, if you go look at the unit test code, and it is public, they will also test how long the whole test took, and they'll see if it was within the acceptable TBU time. So some of your API calls are going to be in these performance tests, and we won't call them once then. We'll call them like 100,000 times. We'll see how long it took. If our implementation took 1 second, your implementation will be allowed 2.5. Hopefully that makes it clear. And that means, yeah, you don't have to worry about, did I have an extra few variables or a few extra statements? That's all fine. As long as you chose good data structures, you're fine. Okay. So this load map, as I said, is kind of important. So what should you do in load map? So a couple of basic approaches. The first one is just do the minimum you can. So it has to do a little bit. In order for you to answer any of these queries that we send to you, you've got to call our lower level API, what we call the libstreet database API. And that API can't answer any questions until you load its data. So if you look through the header files in Milestone 1, you'll see that there are two pieces to that API, and each of them has a load function. Call those load functions before you do anything else, and that means you call them in load map. So you got to do that at least. Okay. But if that's all you did, you just loaded our lower level API and you didn't allocate any data of your own, that's called a stateless interface. You don't make any of your own data. All your functions just call our lower level API and figure out how to interpret the results and formulate an answer. This can be easier to code and debug, but for some calls it's going to be fine. That's exactly the right approach. But for some other functions where we say the performance requirement is high, it won't be fast enough, just because you'll have to make many calls to the underlying straight database API to try to figure everything out that you need and to put it in the right format. So that'll just be too slow for some calls. The other approach is load map actually creates some new data structures, so it does more work. And now you can use those data structures to speed up any API calls you want. And you can mix this. So when the lower level API is fast enough, you can just call it. When it's not fast enough, your load map allocates some additional data to make your functions faster. So you're going to have to do some of this. So I'll tell you right now that you can't pass all our speed tests without loading any data. My suggestion is do option 1 first for every function. So code it in the simplest way you can, just calling our lower level APIs. If it If they're only functionality tests, then you're done. If the performance tests are easy, then you're done. If the performance tests are hard, it's high performance required, then that solution is not going to be good enough. You'll have to recode it using approach 2, but you can build off the code you did, the simpler code, to make that go. So this is kind of a way to divide up the work, which is always a good idea in any project. It's hard to get things working. So if you can get a simple thing working and then iterate to make it faster, that's better than just trying to do everything at once. Okay, I already mentioned this. Load map is speed tested as well. So it can't be too slow, it can't be infinitely slow, but the time limit is pretty loose. It's several seconds, and for bigger cities it's more. So we give you longer for Tokyo than for Toronto, because Tokyo has a lot of streets and intersections. So as long as you, basically load map, as long as you're order n or a bit higher, a little more, you'll be fine. So n again is like number of intersections, number of street segments. If you did something that was order n squared, okay, that grows pretty fast quite quickly. That would turn into, when n is hundreds of thousands or millions, something that's order n squared could actually take an hour. So that's going to fail. But if you keep it at order n or a little more, meaning you kind of go through all of the data we give you a limited number of times, it's going to be fine. Okay, so let me give you an example of this. So one of the functions you have to write for milestone 1 is find intersections of street. So the input is an integer, and because we're using this named street index, which again is just a type def, it's an alias for integer, but this tells us that it's actually, this function takes an integer which is the ID of a particular street. And what we want to return is a vector of intersection indices. Now intersection indices are also just integers, but again we're using a descriptive type def here. So I want to get a vector of all of the intersection IDs that occur on that street. So let's say I'm taking Yonge Street. Yonge Street has many intersections. I want the IDs of all of them. Maybe Yonge Street's ID is that it's street 1000. I want to get back the IDs of all of its intersections. Maybe this one's 50,000, maybe this one is 22,000, and so on. So I want all those in a vector. Okay, so first thing you want to do is you go, okay, well I'm going to query the lower level APIs that I've been given. So the streets database API, it has a header file. One of the most important header file is got this name. And if you look in that header file and you read the Milestone 1 handout, you're going to see that there is a nice function that allows you to ask a street segment what are the two intersections on its end. Okay, so street segment is the length of a city block, and it has a from intersection and it has a to intersection, and it can tell you what each of those are, tell you their IDs. Streets do not have a function that tells you what are my intersections. A street can tell you, well, basically streets don't have many functions at all, actually. What you have instead is a street segment also knows what its street ID is. Okay, so a street segment can tell you I am part of street ID 1000, which means I'm part of Yonge Street, and it can tell you what its two intersections are. So maybe it's intersection 50,000, and maybe it's intersection 22,000. That's what I would get back for this particular street segment. Okay. And let me erase some of this so you can see the animation. But yeah, so that's Yonge Street, and Yonge Street is really not represented very directly in Streets Database API. Instead, what you can do is you can ask street segments, what is your street ID? So you'll find that there are a bunch of street segments that say their street ID is 1000, which corresponds to Yonge Street. Okay, so I'm going to put you in breakout rooms. I want you to try writing it. This is it's the find intersections of street API. One of the things you have to write in Milestone 1. You're going to need to call some functions from Streets Database API. So here's some of the functions that are going to be useful to you. So there's a function that tells you how many street segments are in a city. So for Toronto, this is something like 200,000. So it's a lot. You can also get a structure called street segment info that gives you information about one street segment. And you ask for that by ID. So you could say, give me the information structure for street segment ID 0, or you could ask for ID 1, or you could ask for ID 10,000, all the way up to, say 200,000, whatever the number of street segments are in this city. And then this street segment info data structure has a bunch of public data members. So a structure and a class are basically the same thing in C++. A structure just defaults to all of its members' data and functions are public. So often when you want to just make the data public, you call it a struct. That's what we've done here. So this has a few pieces of data. The only pieces you care about for this exercise are what I just showed you. There's a from and a to intersection ID. So the IDs of the two intersections on the ends of the street segment. And there's a street ID. So it also knows the ID of the street. And notice that the function that you're writing, a street ID is being passed in, because you're asking, tell me the intersections on this street. You're going to get that. You can't just ask Streets database what is the answer to that. It doesn't have a function for that. But it can tell you how many street segments there are, and for every single street segment, it can tell you what is its street ID and what two intersections is it connected to. Okay, so I'm going to put you in breakout rooms. And I'll give you, 3 or 4 minutes, say 4 minutes to try to come up with some code. It can be kind of a little bit abstract. You can write parts of it as kind of pseudocode. Well, do this, loop over that. That's fine. What is your idea of how you're going to do this? And then we come back, tell me if you were able to do it as a group. And if you're comfortable with it, type your pseudocode into the chat or copy it from a text editor into a chat. Could be perfectly correct code if you want, but if it's kind of half pseudocode, that's fine too. All right, so let me put you in the breakout rooms now, and let's see how this goes.
This meeting is being recorded.
Okay, great. Welcome back, everybody. And that was the least painful breakout room management we've had thus far, so that's great news. Anybody want to type in the chat, pseudocode or real code for how you attack this? So pseudocode can just be like, what's your basic approach? Okay, so I see one here. So find any street segment for this street. Use the ID to find the intersections, find other street segments connected to it for each of them. Oh, okay, this is an interesting algorithm. If the segment has different street ID, return with nothing. If it's the same one, return that. And then return a collection of all returned results. So that's actually a pretty interesting algorithm by Sage. It basically goes and looks through to find a street segment that's on the street, and then basically tries to follow it. Yeah, so that's an interesting one. Let's see, so Minghao's got one here, and it's basically getting them street segments. And I think, Minghao, your code is going to put all the intersections and all the street segments together. So it's not going to find the intersections for just one street. So yeah, a few different approaches there. Let me go on and show you what the solution that I came up with is. Okay, so my solution is this. Declare a vector for my result. Okay, so I need a vector of intersection indices, so I declare that, call it intervec. I'm going to get the default constructor, so it's going to start out empty. Now I'm going to loop over all the street segments, and I can do that by going from 0 to the number of street segments, minus 1, so I'm going to use less than to make sure I don't go past the valid street segments. And I'm just going to keep incrementing my counter variable here. So I'm going to go through all, say, 200,000 street segments in, say, Toronto. And for each one of them, I'm going to say, okay, give me the street segment info for that street segment. So I get this data structure, and I call it SS info. And I'm going to check if SS info, if it's street ID, so this street segment knows what street it's part of. So if its street ID matches what was passed in, then you're part of the street that I want. So if your street ID is, say, 1,000, then you're part of Yonge Street. I was asked to find all the intersections for Yonge Street, so I'm going to pay attention to you. And I didn't write the code here, but basically I should add these from and to intersections to my intersection vector. Maybe I have to be careful that I don't get duplicates. Maybe I would add them twice. So I got to write some logic there, but this will work. Now the next question is, and yeah, you have to think about what to do in terms of be careful about duplicates. So you read the header file carefully to see should you have duplicates. If you actually read it, it indicates, doesn't seem that it wants duplicates. So you can check. There are various ways you can remove duplicates at the end. So probably what I would do is just add them all in and then remove them at the end. But there are other ways you could do it. So once I'm done, I return this intersection vector. Now, the next question is, what's the computational complexity of this? This is actually a very reasonable way to do it. Okay, I think with the APIs we give you, you can't do it any faster than this. So what is the computational complexity of this? Yeah, so I see various people saying order n. Well, let's see, we've got a loop, and it does go through n times, where n would be the number of street segments. And most of these street segments are actually not interesting. They're not on the street we care about, but we still have to look at them and check their street IDs to see maybe we do care about them. But you know, in a big city like Toronto, probably 1% or 1 in 10,000 maybe for a short street of these street segments actually is of interest to us. But we're going to look through them all anyway. So it's going to take us a bunch of time. So this isn't that fast. And there are questions about whether Sage's solution is going to be faster, the recursive function. I don't think it is. The reason is to find the starting point, like to find even one street segment that is on the street, he's going to need a loop like this. Okay, he doesn't know where to start his recursive solution. He has to go through all the street segments trying to find at least one that's on the street, and then he can recurse. So in general, let's say for short streets, he's going to have to go through maybe half the street segments in Toronto before he finds one street segment that's on the street. So his computational complexity is also order n. Okay? So it's not very fast, but it is going to work. All right. Is that the fastest possible? So I just showed you with the API that we've given you, you can write code to do this in order n computation. Could it be done better if you were allowed to store some data? Okay, so what do you think? You think it's the fastest? It is the fastest you can do. Like it's order n with the API we give you. But in load map, you can load additional data. Okay? So by pre-computing something, there are a bunch of different things you could do, but pre-computing data in load map, the fastest possible you could do is you at least have to store all the intersections on the street so that you can return them. But if you actually pre-computed that in load map, you could just return all these intersections. So the fastest possible would be order number of intersections on the street, because you could just return them. Now that means load map did some more work, but we don't really care about that. So, and this is a much smaller number. So the average street probably only has 2, 5, 10 intersections on it. It's not that long. Even a really long street like Yonge Street has a small fraction of 200,000 intersections on it. So your average complexity is much, much faster. But you're going to have to figure out how to write something in load map in order to make it faster. Okay? So that's all I'm going to say about that function. You can follow that idea to get a basic implementation. You have to think about what to put in load map to get a faster one. You now need to clean up. So remember to clean up your memory at the end in your close map function. We'll always call that once we're done doing a bunch of queries in a city. The way ECE 297 exercise work is it always does this sequence of load map, use things, and then close map. And we do run, one of the tests runs valgrind. So if you leaked memory, we're going to find that in the valgrind test because your close map didn't clean up the memory used. Now, cleaning up memory is a lot easier if you use STL. because STL has proper destructors for everything. If you use vectors and maps and so on, your closed map doesn't have to be very complicated. If you start going nuts with pointers, and you call new yourself a lot, well, then you're going to have some delete calls in your closed map. But it's better to try to use STL and try to not use new and delete a lot. Let's see, there's a question from Sage. Won't load map fail performance? You can compute a lot of stuff in order n compute. So your load map, don't make it order n squared. But if it's order n to pre-compute things, that's actually sufficient to compute a lot of stuff and it won't fail performance. So hopefully that answers your question. Okay, so we're going to do some automatic memory checking. So we're going to run valgrind on your program. This is actually good practice in software development to always be doing automatic memory and illegal dynamic behavior of your program checking. Valgrind is one of the tools to do that. The other is the debug check build. ECE 297 exercise is going to run valgrind on your program every time you run it. Now valgrind slows down your program by about 10x. So that is a problem. What we want in testing is we actually want two somewhat incompatible things. We want it fast so you can run the tests a lot, and we want it to be thorough, which means we'd like to do each test to make sure it catches all the bugs it can. Those are actually kind of contradictory. So for things like valgrind, where we're checking for illegal memory accesses, a small test case is almost as good as a big one, because we're not testing functionality of all the corner cases. We're just seeing, do you do some bad array accesses? And usually if you do those, you'll do them, most of the time they'll show up in a lot of test cases. So a reasonable thing to do is to run valgrind on a small test case. It's not quite as good as running on a big test case, but it's going to make you a lot more productive because it doesn't take that long. So one of the cities we give you is called St. Helena. St. Helena, this is what Google Maps shows for its road system. Not a lot of roads. Okay, so where is St. Helena? St. Helena is one of the most isolated places on Earth. It's in the middle of the South Atlantic, so that's St. Helena there. Anybody know what else St. Helena is famous for? So it's famous for being isolated. Yeah, it's where Napoleon died. Okay, so Napoleon, after he's defeated for the first time in Europe, he was exiled to the island of Elbe in the Mediterranean. Turned out that wasn't isolated enough because he escaped, he came back, he fought a bunch more battles. So they exiled him again, and this time they put him in the middle of the South Atlantic, and he never got off of there. So as you're looking at these bugs from valgrind and feeling annoyed with St. Helena because you've got bugs in it, think of Napoleon bitterly resented being out in St. Helena so far from the action. So it's not as bad as his situation. Okay, how do we get the data from load map to these functions? So you call load map. Load map is called by these unit tests. It's just past the name of a map or a binary data file. And then we call things like find closest intersection, which is just past a latitude and longitude position. It's not past any other data structure. So how did we, if we stored something in load map, how do we get it to this function so it can use it? And you can't change how this is called, because our unit tests expect it to be called this way. To make sure you don't change how it's called, we made the header function m1.h read only, because you break all our unit tests. So you can't just say I'm going to pass some new parameter to it. Can't change it. So what do? How do we use this? Yeah, so I see Sage saying global variable, and this is exactly right. The way you connect it is with a global variable. So you're going to need at least one global variable in your program to pass the speed tests. And now many of you are probably thinking, well, wait, aren't global variables bad? And they can be. So if you overuse them, they are bad. So for example, if you go, I don't like typing, I'm going to just use global variables so I never have to pass arguments to my functions. That's a really bad reason to use global variables. But almost all programs have one, or something that is very similar. There are a few ways you can make things that are essentially global variables with a little bit of C++ hiding them a bit, but they're basically still global variables. So let me ask you this. What, for example, let's see if I can write more clearly. What is this variable? Okay, what kind of variable is that? Standard C in. And same question for standard C out. Well, they are objects, but objects are just also variables. Yeah, the type is a stream, but is it a local variable? Is it a global variable? It's a global object. So this is a global variable. So you've used global variables in probably almost every program you've written in C++, because if you use cin or cout, they're global variables. So, but they're very logical global variables. Lots of things want to talk to the keyboard or the screen. So C++ makes them global variables because they're so commonly used. So they do exist in almost all programs. You should limit their number. So something that is good code style is grouping related data into classes. So you're going to have a bunch of data that load map creates. You might group that into a class called something like street graph. It organizes your data. So somebody reading your code can see, oh, this stuff all belongs together. There's less namespace pollution. You just have to remember there's an object called street graph, and it's got a bunch of members inside of it. That's easier to remember. And basically now your load map and close map are going to create these global variables, or even better, one global object that combines the variables. And then the query functions, like find closest intersection, are going to use them. So they're going to call into that when they need to speed themselves up. So if you use global variables in an undisciplined way, it's hard to determine what are the actual inputs and outputs of your functions because they're not explicit. They're not in the parameter list. So what you should do is in Milestone 1, all of these query functions like find closest intersection should only read the global variables. They shouldn't change them. And load map and close map should be the only place where you change those global variables. One sets them up and the other, deletes them or clears them. And that's pretty disciplined. That's a logical convention that people can understand when they're reading your program. Okay? So any questions on that? It's kind of how we set all this up. Does it make sense? I'm going to take silence as agreement. This is like a little algorithm I'm going to show you because one of the functions that m1.h asks you to implement is basically the area of a polygon. Features in the API we've given you, the data we've given you, are basically outlines. And we use features to represent things like parks and lakes and streams. So they are important parts of the geography of a city, and they're represented as polygons. So, and we ask you to compute the area of the features because that gets you used to how do you access this data and can also be useful for some things later in the project. But you've got this polygon, and it's an arbitrary, what's called a simple polygon. So simple means no holes. So you never get a polygon that has a hole in the middle. Okay, so that's not going to happen. But it won't necessarily be a rectangle or a triangle. It could be a polygon with 99 points along its boundary. They will always be ordered. Okay, so you can ask for these points, and they'll always come back in order. It won't be in a random order because otherwise you couldn't figure out the boundary. And they're XY points. Algorithmically, how could I figure out the area of some arbitrary polygon like that? Does anybody have any ideas? Integral, break up into triangles. Yeah, it is a form of integration. You could break it up into triangles. That could work too. So I'm going to show you a way that's fairly simple and works well. Okay. So what you do, let's say this is point 0. So the API we've given you, you can ask for how many points are in this feature, and then you can say, well, give me the first point, give me the second, give me the third, etc. So let's say this is x0, y0, first point. And this one is, you ask for the next point, you'll get x1, y1. So if I take y1 minus y0 times the average x, which is just x0 plus x1 over 2, it's like an integration. So people guessed integral, it's a good idea. I just integrated this area, okay? And I keep doing that. So now I go on to the next pair of points, and I just do the same calculation. So I integrate this area, go on to this one, integrate that, go on to this one, integrate. So I'm always getting actually the average, but basically I'm integrating all of these areas. So the next one I'm going to get this area. So Actually, no, I'm going to get this area out to here. Okay, so by the time I've gotten up to here, I've done this integral, but it's too much, right? I've got more than just the shape, but I've not done my points yet. I keep going. Let's see if I can change the pen color here. So let's change the pen color. I go on to this point, and at that point, you'll notice that this y, you know, the higher y minus the lower y, is actually negative. Okay, so I'm now going to get a negative y1 minus y0 because I'm going to take this y minus this y, and that's actually a negative number. And I'm going to multiply that by the average x, and I'm basically going to get a negative number, and it's that. And then I go on to this last one, and I'm going to get another negative number. And the summation of this basically is the area of the polygon. I basically figured out the integral. How far am I from the x-axis, and that's too much area as I'm going up, but as I come back down the other side, I subtract off all of the essentially integral of the space from the other side of the polygon to the y-axis, and it works out. Okay? If you went around the points in the wrong order, you get a negative area. That's fine. If you ever get that, you just say area can't be negative, multiply by -1. This works for any simple polygon. So it will not work if you have holes in the middle. Then you have to do something more complicated. We'll never give you a polygon with holes in the middle. Okay? No, this is a known algorithm, but it's basically I'm telling it to you because I don't want you to get hung up on like how do I do this? You're giving me like 250 point polygons, and I'm trying to break it into triangles. There's a pretty simple way to do this. Okay? Let's see. You don't have to sort the points. We give you the points in the order of the polygon. Otherwise, you can't figure it out. If we just gave you points in a random order, you can't figure out what it is. And let's see. So and that is what a feature looks like. So I should have done that before. Okay, so a couple minutes left. Let me talk about team formation. That basically, we've talked now about what do you have to do for Milestone 1. Between the tutorial and the last 2 lectures, hopefully you know enough to get going and read the handout. You're going to do this in a team. So a few words, and we'll keep talking about this next lecture, but a few words about forming a team. So I believe you studied this in APS 112, 111, 4 stages of a team. Okay? Type in the chat if this is looking familiar. Have you seen this before? Bruce Tuckman, psychology professor, came up with 4 stages of a team. Okay, so you see lots of yes. So I'm going to go through this quickly, but this is actually something I first saw in management training when I was at Altera. And it was useful. It resonated with me. So the first stage is forming. You know, you're just picking the team. You've gone through that. Second stage is storming, figuring out who does what and how. It's often contentious. So you may have some conflict early on, trying to figure out who does what, and there's no general agreement. Don't be worried about that. It's normal. Okay? You do want to get through it, but don't be scared. Norming is now people they're getting into a groove. They understand their roles. They're accountable for, you know, their part of the project. You're working together pretty well. And the highest stage of performance, which many teams don't get to. So again, when we went through this in management training with essentially as management consultants, basically going through how can you be more effective. Lots of teams, even in industry, never get here. Okay, it's where you want to get, but not everybody does. And basically, in these team members not only know how do we get things done, they're continuously looking for how to improve, okay? And the way they do that is they discuss things openly, and to discuss things openly, you actually have a pretty trusting relationship. And it takes time to get there. You may not get all the way to number 4 in this project, and that's okay, but you want to at least get to number 3. And through your career, when you're on a team, you think of how can we be high performing, which means it's not enough just to be accountable for your role and knowing your role. You actually need to have this attitude of how can we do better, let's discuss openly. And you do that in a positive way, which is what creates the trust so that people actually pay attention to you. Okay, so you're here, and you want to at least get to stage 3, but hopefully you get to stage 4. Okay, how can we get there faster? So this takes time. It doesn't happen overnight. You have to build that trust. You have to find those norms. You have to go through that discussion, that continuous improvement to find good ways to work together. And again, in industry, when you're making teams, it never ends. Teams keep trying to get better, and their role keeps changing, so they need to keep improving. But how can we speed this up? You're not in a project for that long. You don't want to waste a lot of time in these earlier stages of storming, where nobody knows who's doing what. So any ideas? It's the last question I'm going to ask you this lecture. How can you get to I've only got one idea here. Okay, so how do you get to a higher performance thing? So I see Daniel saying dictatorship. That actually doesn't work very well. I had some interesting discussions when I came back from industry to U of T, where I had some professors saying it must be nice to be in industry where you can just tell people what to do. Because like, I had more than 100 people reporting to me. I very rarely said do this because I'm the boss, because it's a very weak form of management. So yeah, even when you have the power to coerce people, if you're a good manager, you very rarely use it. So any ideas? I'm going to give you a second and they'll go on. So it's not dictatorship. Yeah, be open and upfront about your strengths and weaknesses. That's really good. Open communication. Yes, these are all good ideas. I'm going to tell you something though. To get going, my advice is meet and work together right away. Okay, so normally you do that in the lab, share a meal. When I was building new teams in industry, working with people often at different sites, I'd take them out to dinner. Right? I need these people to work with me. We need to build a relationship fast. I'd fly out there. I'd maybe bring part of my team out, and we'd go out to dinner. And you got to start building that trust right away. Okay, you can't do that right now. So your next best is you got to work in Zoom, but work together in Zoom. You might be tempted to say, well, why do that? We'll just like send each other some emails, and we'll do our work, and we'll never see each other. Human beings build trust by seeing each other, by being around each other. So ideally you'd be doing this, right? You'd be getting together in person and spending some time together. You can't do that right now, but have a Zoom meeting, even if you're all sitting there coding away and you're just chatting some now and then, do that, okay? So that's my last comment. I see some teams do this for sure, and it tends to build a higher performing team faster, and some people don't believe what I'm saying here, so they try to do it without any contact with their team members. They just try to do it by email. It's not a good idea. You want to build this trust fast, so have some Zoom meetings. As I said, even if it's like you're in a Zoom meeting and you're all coding away and just saying things to each other once in a while. This link is to an interesting story in the New York Times, which you should be able to access for free if you haven't been clicking on the New York Times a lot. I'll try to find other ways at it too. Read it. We'll discuss it in the next lecture on Monday. It's one take on some Google research, some research Google did on what were properties of their most successful teams. So interesting article. We'll talk about it on Monday. And that's it for the lecture. I'll hang around in case there are questions. And have a good night, everybody.